Hello Professor, my name is Farzana Bony. My project paper name is Orion, a distributed file system for non-volatile main memories and RDMA-Capable networks. Now I'm going to the next slide. Here is my outline of my presentation. I will discuss these topics in my presentation. Going to the next slide. Now I will explain the abstract part. In this paper, the abstract represents a special distributed file system named Orion for non-volatile main memory, its short form NVMe, and remote direct memory access, its short form RDMA networks. Traditional design optimized for slow and block-based storage now face critical bottlenecks in networking and software overhead when using NVMe. Although traditional file systems have many benefits, Orion seems to outperform many of these due to flexibility, reliability, and effective data transfer rates. The designer needs to take careful consideration of complex optimization, batching, queuing, and other operations. This paper introduces a distributed file system specialized for NVMe storage, leveraging RDMA-based networking to optimize metadata and data access while maintaining NVMe's byte address ability. The Orion file system uses RDMA whenever possible to make sure that the CPU is not involved in transfer all the time. It results in lower CPU usage and improves scalability performance. Now I'm going to the next slide. Introduction. Orion file system is developed for faster data processing and high throughput by using NVMe and RDMA networks. The key innovation include low latency, scalable performance through a unified file system and network operation, efficient metadata update mechanism, log structure consistency maintenance, and support for direct access. The Orion also enhances reliability and availability through metadata and data replication. The traditional distributed file system designed for block-based device primarily optimized for the slow performance of disks, focusing on complex techniques like queuing and batching. This paper introduced Orion, a distributed file system architecture from the ground up to leverage NVMe and RDMA networks. Orion is different from the traditional block-based design by deeply integrating RDMA and optimizing for NVMe characteristic, achieving performance parity with local NVMe file system and significantly outperforming existing distributed file system. The key focus area include reducing software overhead, enhancing network performance, and supporting NVMe byte address ability, ensuring Orion maximize the potential of NVMe technology and outperform the existing distributed file system. Now I'm going to the next slide. Now I will discuss the motivation of this paper. Orion is motivated by the emergence of non-volatile main memory and remote direct memory access networking technologies. NVMe offer persistent byte addressable storage with performance close to DRAM, drastically outperforming traditional storage device. However, the existing distributed file system failed to fully exploit NVMe potential due to their design for block-based storage. These traditional systems suffer from inefficiency in software overhead, network performance, data replacement. Orion addressed this challenge by integrating RDMA deeply into its architecture, minimizing the software overhead and optimizing NVMe characteristics. This ensures low latency, scalable performance, and efficient metadata management, fully leveraging the capability of NVMe and RDMA. Now I'm going to the next slide. Now I will talk about the main purpose of this study. The main purpose of this study was to introduce Orion, a fully featured system that can replace the traditional file system with faster processing, less dependency on CPU, optimized task scheduling, and many other benefits. The author were hoping to introduce a combination of NVMe and RDMA network-capable file system that will eliminate the two-layer of abstraction used in traditional system, causing overhead and inefficiency. NVMe provide a faster data transfer rate and RDMA network ensures very low latency. The combination of this is essential for an effective file system. Although NVMe and RDMA network have their own drawback, Orion brought them together by providing a unified file system that can achieve high level of performance. Now I'm going to the next slide. Now I will explain some key definition from this paper. The author did not provide any new definition throughout the paper. However, they discuss different keywords. NVMe, it means non-volatile main memory. NVMe consists of non-volatile DIMM that are attached to a CPU bus that has traditional DRAM, DIMM as well. These are commercial products relying on DC battery power to operate. RDMA, it means remote direct memory access. It refers to the network capability where data access can be provided remotely, allowing for one-sided read or write or both-sided send and receive operation. It can also allow both kernel level and user level remote instruction. Byte address ability. The author frequently uses byte address ability to explain the capability of NVMe that lets them use byte addressing. So integrating Orion does not impact their performance nor does it hinder faster data processing. DAS. DAS is a short form for direct access. This is a unique feature that can grant direct access to NVMe bypassing the page cache. This enables direct load and save memory operation to be performed on NVMe. DAS is a crucial feature for speed improvement in NVMe and determining factor in its higher performance over a traditional storage option. Now I'm going to the next slide. Now I will talk about some related work in this paper. Orion combined concept from NVMe file system, distributed file system, distributed shared memory, user level file system with trusted service and RDMA optimization. The first point, NVMe file system. Nova inspired Orion metadata management techniques. Orion built on many concepts and implementation detail from Nova, particularly in metadata storage and updates, and incorporate valuable insight from several earlier systems. Emerging NVMe technology have led the researcher to develop various NVMe specific file systems. The second point, distributed file system. There are two main approaches to providing distributed file access. Deploying a cluster file system, one block device using SAN protocol, and building a distributed file system that combines local file system on multiple servers into a single shared system. Orion rethinks this design to fully exploit NVMe and RDMA characteristics, outperforming systems like Octopus, which has limitations in complexity, locality, and replication capability. Orion improves data locality by migrating data to local NVMe and support complex workload and replication for better fault tolerance. Third point, trusted file system service. A recent research trend involved decoupling the file system control plane and data plane to create user space file system with trusted service, reducing the number of syscall. Orion metadata server functions similarly but leverages the kernel file system mechanism, including linear addressing of kernel virtual and DMA addresses. Supporting DAS accesses in a distributed user space file system introduces challenges such as managing large page table, sharing protection across the processes, and handling page faults which are not compatible with RDMA. The fourth point, distributed shared memory. Hotspot is a distributed shared memory system that allows application to commit fine-grained objects on memory map NVMe files using a customized interface requiring application modification. It uses multi-stage commit protocol for consistency. In contrast, Orion ensures file system consistency through the client-side update. Additionally, Orion employs Mojim fine-grained replication technique for NVMe to implement metadata replication. The fifth point, RDMA optimized application. Many existing work explored the use of RDMA to accelerate the data center applications such as key value store, distributed transaction system, distributed memory allocator, and RPC implementation. Orion differs by handling network requests directly within the file system routine and using RDMA to fully exploit the byte address ability of NVMe as optimizing performance and efficiency. Now I'm going to the next slide. Now I will talk about the design overview. Orion is a distributed file system built for the performance characteristic of NVMe and RDMA networking. NVMe low latency and byte addressability fundamentally altered the relationship among the memory storage and network, motivating Orion to use a clean state approach to combine the file system and networking into a single layer. Now I'm going to the next slide. I will explain some design goal of Orion file system. Orion file system has some design goal. The first goal, scalable performance with low software overhead. Scalability and low latency are essential for Orion to fully exploit the performance of NVMe. The second goal, efficient network uses on metadata update. Orion caches the file system data structure on client. A client can apply the file operation locally and only send the changes to the metadata server over the network. The third goal, metadata and data consistency. Orion uses a log structure design to maintain file system consistency at low cost. Orion allows read parallelism but serialize the update for file system data structure across the cluster. The fourth goal, dark support in a distributed file system. Dark style direct load store access is a key benefit of NVMe. Orion allows client to access the data in its local NVMe just as it could access a DAS-enabled local NVMe file system. The fifth goal, repeated access become local access. Orion exploit the locality by migrating data to where writes occur and making the data caching an integral part of the file system design. The sixth goal, reliability and data persistence. Orion support metadata and data replication for better reliability and ability. The replication protocol also guarantees the data persistence. Now I'm going to the next slide. Now I will talk about cluster organization. Orion cluster include a metadata server, several data store organized in replication group and client all connected via an RDMA network. The MDS manage the metadata and maintain RDMA connection with client and facilitating the propagation and retrieval of updates. Orion allows client to manage and access a shared pool of NVMe with data residing on a single or multiple DS. Client use one-sided RDMA for remote access and load and store instruction for local NVMe. Orion support both metadata and data replication with the MDS potentially running as a high-ability pair using MOSIM-style replication. DS in replication group have identical data layout and Orion employs broadcast replication for data. Now I'm going to the next slide. This figure shows the architecture of an Orion cluster. Orion cluster consists of a metadata server, client, and data store. Now I'm going to the next slide. Now I will talk about software organization. Orion software run on both the client and metadata server, exposing a process interface utilizing kernel module to manage file and metadata in NVMe and handle MDS client communication. These design avoid the overhead associated with the conventional two-layer system. Orion inode contain the pointer to metadata log which store modification and data block pointer. These logs are copied to the client, simplifying metadata management, enable local application of log entity before propagating changes to the MDS. Data is distributed across DS and replicated within the group with global page addresses used for locating data. Client can read from any node in a replication group and perform copy on write for data update. Orion also maintain a client-side data cache to enhance the data locality, bypassing the operating system generic page cache and managing DRM directly. Now I'm going to the next slide. This figure names Orion software organization. Orion exposed as a log structure file system across MDS and client. Client maintain local copies of inode metadata sync with the MDS and across the data at remote data store or local NVMe directly. Now I'm going to the next slide. Metadata management. In distributed file system, metadata updates are crucial as they often lie on an application critical path and rapid handling of metadata requests. Orion metadata server manage all metadata updates and persistent copy of metadata. Now I'm going to the next slide. Now I will talk about metadata communication. Orion metadata server organize metadata communication and handle all metadata updates. Client use three methods to communicate with the MDS and depending on the operation complexity. Method 1. Direct RDMA read. This method is used for maximizing MDS scalability. Speculative and highly optimized log commits. This method is used for committing changes. Method 3. Acknowledge remote procedure call. This method is used for complex operation. This method range are from simple to complex, ensure efficient and scalable metadata communication in Orion. Now I'm going to the next slide. This figure name Orion metadata communication. Orion maintain metadata structure such as inode log on both MDS and clients. A client commit file system update though log commit and RPC. Now I'm going to the next slide. This figure name MDS request handling. The MDS handle the client request in two stages. First, networking thread handle RDMA completion queue entities and dispatch them to the file system thread. Next, file system thread handle RPC and update VFS. Now I'm going to the next slide. This figure name metadata consistency in Orion. The inode log on client A is consistent after updating the log entry committed by another client using RDMA read, issuing a RPC and rebuilding the log on conflicts. Now I'm going to the next slide. This figure name Orion data communication. Orion allows client to manage and access data independently. This figure demonstrates Orion data access mechanism. A client can request a blockchain from the MDS via RPC. Step 1. When client open a file, it builds a registry for faster lookup from the file offset to log entities. Step 2. When handling a read request, the client read from the DSP to its local DRM and update the corresponding log entry. Step 3. For a write request, it allocates from its local chunk. Step 4. It ensures that data reaches to its local NVMe DSC. Step 5. Then a log entry containing information such as the GPA and size is committed to the MDS. Step 6. Finally, MDS append to the log entry 7. Now I'm going to the next slide. Now I will talk about Orion evaluation. Orion evaluation demonstrates its great performance compared to the existing distributed file system. By leveraging NVMe, RDMA, Orion achieved low latency metadata and data operation with performance close to local NVMe file system. The system shows excellent scalability, handling increased client load efficiently. In benchmark, Orion outperformed traditional system, particularly in parallel workload. The integration of RDMA and NVMe optimization proved effective and highlighting Orion potential for significant improvement in distributed file system design. However, further real-world testing and evaluation of long-term stability and security are necessary for a comprehensive assessment. Now I'm going to the next slide. The first figure name is application performance on Orion. The graph is normalized to Nova and the annotation gives Nova's performance. For write intensive workload, Orion outperforms by a wide range. Second figure name is Orion data replication performance. Updating a remote replica adds significant to random write latency, but impact on an overall benchmark performance is small. Now I am going to the next slide. Now I will talk about finding or outcomes from this paper. Orion, a distributed file system designed for NVMe RDMA network, significantly outperforms existing distributed file system by leveraging NVMe byte address ability RDMA low latency communication. It achieves performance comparable to the local NVMe file system while maintaining high scalability and low software overhead. Evaluation result shows that Orion provides sustainable performance improvement for metadata and data operation, offering higher performance in parallel workload than traditional system. The integration of RDMA and NVMe in Orion represent a successful rethinking of distributed file system design and optimizing for the latest software advancement. Now going to the next slide. Now I will talk about strengths. The biggest strength of Orion is its ability to combine two layers of abstraction into one. This increases efficiency. It achieves low latency and scalable metadata and data operation by unifying file system and network layer, reducing software overhead and optimizing for NVMe byte address ability. Orion uses RDMA read, optimized log commit, and to ensure efficient metadata management. It client-side caching and data migration enhance data data locality, while MOSIM-style replication provide reliability and availability. Evaluation results shows Orion outperforms the existing system by a large margin. Orion imposed the high performance of NVMe RDMA network, resulting in significant improvement over a traditional distributed file system. Now I'm going to the next slide. Now I will talk about limitation. Orion design may face scalability challenge in extremely large deployment due to the single MDS structure. Additionally, reliance on MDMA and NVMe means its performance benefits are tightly coupled to the ability and specific characteristic of this advanced hardware technology. Now I'm going to the next slide. Now I will talk about future work. Point 1. Long-term stability and reliability. As Orion is still its early state, it requires update to become a mature and commercialized product. Ensuring sustainability among rapid technological changes is crucial. Point 2. Regardless testing and verification. Orion needs to undergo more extensive testing and verification by third-party user. Focus on data management integrity is essential. Point 3. Impact on cloud infrastructure. Investigating how implementing Orion in data server and cloud cluster will affect current cloud infrastructure. Point 4. Security aspects. Future research should explore the security implication due to the distributed nature of Orion. Point 5. Benchmarking in diverse environment. Beyond the lab experiment, Orion should be tested on various platforms to assess its performance under different conditions. Point 6. Energy consumption. Evaluating the energy consumption rate for Orion in high-paced parallel computation tasks with frequent memory access. Now I'm going to the next slide. Conclusion. Orion represents a significant advancement in distributed file system design, especially for the higher performance capability of NVMe RDMA network. By integrating RDMA deeply into its architecture and optimizing NVMe, Orion achieves low latency, scalable metadata data operation, outperforming existing distributed file system by a sustainable margin. The innovative use of client-side caching, data migration, MOSIM-style replication ensures both high performance and reliability. While initial results are promising, Orion long-term stability in diverse environments requires further exploration. Future research should focus on enhancing its maturity, conducting rigorous third-party testing, and investigating its impact on cloud infrastructure. Additionally, addressing security concerns and evaluating energy consumption in high-demand scenarios will be crucial. Overall, Orion set a new standard for distributed file system, fully leveraging the potential of modern hardware advancement. That's all my presentation. Thank you, Professor.